Chapter 4, Fundamental Research Issues. In this video lecture, it is my hope to help identify some of the most critical areas for students to understand moving forward and to help give you some tips to help keep confusing terminology straight so that we address the most confusing aspects of research methodology. Once again, here's the disclaimer. I assume that you already know not to use class materials for anything beyond this class. The learning objectives for this series of slides will address the various types of validity, such as construct, internal, external, and statistical. We're going to talk about what variables are and how to describe a variable in a study, which is what we call an operational definition of a variable. We're going to talk about the different types of relationships that variables tend to have, such as positive, negative, curvilinear, and no relationship, as well as what these might look like on a graph. We're going to talk about some strengths and weaknesses between non-experimental and experimental research methods. One of the most confusing aspects of research methods that students repeatedly have difficulty understanding is the difference between an independent variable and a dependent variable. So we're going to talk about that a little bit here as well, and maybe help clarify and hopefully unconfuse you. Finally, we will talk about the strengths and limitations of laboratory experiments and the advantage of using multiple methods of research. So since we are going to be talking a bit about validity here, I wanted to also introduce you to a term called reliability first. When we think of a person who is a reliable person, we are thinking of an individual who we can count on to always do what is expected of them. The same is true for research methods. If we conduct a particular experiment or use a specific type of questionnaire or some type of apparatus that is reliable, then we would expect to always get the same consistent results. But you cannot have valid results on any level without first having reliable results. So think of it this way. If I aimed a bow and arrow at a target and every arrow hit in a different place, this would be an example of lack of reliability. However, if I aimed the same bow and arrow at a target and every arrow hit in the right upper hand corner, it would be reliable because it's heading in the same place every time, but it would not be very valid because it's not hitting the bullseye. Going one step further, if I hit the bullseye every time, then I would have a method that is both reliable and valid. So as you can see, just because something is reliable, it does not mean that it is valid. And we can't have a valid method of doing something unless we know that it is going to be reliable first. So this is a confusing topic in research methods, and I think it's helpful for folks to try to begin wrapping their brains around it. And I try to use that example of the bow and arrow because I think it's something that you can picture in your mind that is going to easily reflect the notion of accuracy or trueness, which is, of course, what validity is all about. Generally speaking, we're concerned with 4 types of validity for the purposes of this class. The first one is construct validity, which is the extent to which we are actually measuring something we are trying to measure. One example of construct validity that has been extraordinarily difficult to measure has been autism. So in years past, researchers tried to divide up autism into smaller categories and then assigning those categories names such as Asperger's. Truthfully, autism captures such a wide array of symptoms and limitations that these categories did not always seem to be very accurate. So as a result, experts decided to collapse all those categories into one bigger category of autism in about 2015 or so. So what we have now is a very broad category of different types of symptoms and limitations that probably captures more people with autism, even though it is probably less descriptive for each individual. In other words, construct validity for autism appears to be an issue that the scientific community is still trying to work out, because our understanding of what it means to be autistic also is evolving. Next is internal validity. What this refers to is the extent to which we can make an accurate statement about cause and effect relationships based on the type of study we conducted. We'll try to talk about this a little bit more later in these slides, but it should stand to reason that some studies are relatively weak in terms of being able to clearly show a cause and effect relationship, whereas other designs are much stronger. External validity is sometimes seen as the opposite of internal validity, although this is not entirely true. External validity means the extent to which the results of a study can be reasonably applied or generalized to other populations and settings. One easy to understand example is that if we develop a personality test that is standardized on most of the population in the United States, and even if we do a relatively good job of capturing different age groups and different ethnicities and so forth, that we will still have some trouble applying that same personality test to individuals who might come from a different part of the world. For example, I've completed evaluations with people who are refugees from war-torn countries in Asia and the Middle East, and it is not unrealistic, or I should say it's realistic, to expect that the test would be measuring something different for these individuals as opposed to individuals in our country who come from a different cultural background. So the reverse can also be true, that some research suggests that there are certain universal aspects to the psychology of all people, regardless of where they come from and what their experiences might be. Finally, statistical validity refers to the relative accuracy of the statistics being used in a particular study. Hopefully you have already successfully completed the intro statistics class, because that's going to help you with your understanding here. If you remember from your statistics class, there are different kinds of statistical tools we can use to analyze data, depending on what kind of questions we're asking. In some cases, researchers use appropriate statistical tools to try and understand the data, but sometimes they might make mistakes or inappropriately apply the wrong tool. And so then they eventually get inaccurate results and conclusions. So let's think about what this example would be. What would you think if you read a study on the safety of a particular type of medication and the study results suggested that it was safe, but after you read the study more deeply, you found out that the researchers did not apply the correct statistical procedure to analyze the data? Obviously, this would be a serious problem in reality, and this would be a question of statistical validity. Variables are what we want to pay the most attention to in our research, and this is ideally what we're observing or measuring. Some qualities are relatively easy to translate into a variable, whereas other characteristics might be more difficult or even impossible in some respects to try and translate into some type of value. At the most basic level, a variable should have at least two values, and one easy way to think of this is whether a question could be answered as a true or false or a yes or no type of response. But not all questions can be answered with a simple yes or no, which is why some questionnaires have alternatives in the middle somewhere, such as sometimes, most of the time, rarely, and so forth. Researchers will make attempts to translate these responses into numerical differences so that they can be analyzed statistically. There are also situations where translating a particular response into a number may not make a whole lot of sense, such as categorizing one's eye color or other descriptive elements. At the simplest level, variables can be characterized as quantitative, meaning that there is a numerical value such as age, IQ, and so forth. Qualitative variables mean that the numerical value does not really translate to a specific human quality, like happy or sad or attractive or unattractive. One of the most important things to understand about variables is their operational definition. The reason why this is important is because having an operational definition provides readers and other researchers with a standardized way to know what it is that you're talking about in your study design. So, for example, if I wanted to do a study on children with severe depression, I would first have to operationalize what I mean by children by specifying a specific age group and also maybe talking about the types of children that I would include in my study that could meaningfully participate. I would also have to operationalize what I mean exactly by severe depression. In other words, Would this mean kids who scored highly on a depression questionnaire? Or would this mean kids who show repeated severe signs and symptoms? Or would this mean something else? As we try to explain our reasoning in our research proposals, these operational definitions become exceptionally important, because if we don't do it, we risk having unfair comparisons made from study to study. From a statistical standpoint, what we are really interested in are the relationships between values that we can observe. So let's talk about what kinds of common relationships we might see. The first is a positive linear relationship. So let's say, hypothetically, that a person with schizophrenia would show increasing positive benefits with increasing amounts of medication. What we would see in a graph is a level of improvement going up while also the medication levels are going up. A negative linear relationship could also exist in the same patient population depending on what we're measuring. So, for example, if we wanted to look at increasing amounts of medication and decreasing levels of symptoms, we would see a negative relationship here. In other words, as medications go up, symptoms of schizophrenia go down. Truth be told, it is unusual to see perfectly linear relationships in actual research, but when we do see something that is more linear, this is an important finding for sure. Typically, what we see more often are curved lines in these relationships, and we call these curvilinear relationships. So let's talk about what an example of that might look like. If you imagine for a moment that an athlete wanted to use a performance-enhancing drug like some type of stimulant, for example, for the purpose of getting a better performance. Initially, we might see that medication or performance-enhancing drug level increase, and then their overall performance would increase as well, but only to a certain point. At some point, the relative improvement from the performance-enhancing drug levels off, and the athlete continues to use more of it, expecting better results, but the performance actually suffers and gets worse over time. So what you would see here is something like an inverted U, where initially their performance goes up, but then reaches a point where the gains are maximized and then begin to actually go the other direction, falling back down. Finally, there are certain situations in which we would measure two variables and see absolutely no relationship at all. Believe me, this does occur from time to time. What this would look like on a graph is a flat line, horizontal, or potentially a perfectly vertical line. So what this would mean is that as one variable increases, the other variable does not change at all. For those students who might benefit from seeing what these relationships look like on a graph, you can see those relationships here. On the upper left is that positive linear relationship characterized by a flat increasing line moving upward, and the negative linear relationship on the upper right side with the trend moving straight but downward. On the lower left is that inverted U I was referring to with the athlete example, and on the lower right is the flat linear line that reflects no relationship between the two variables. Relative differences exist between non-experimental and experimental methods. Most of the research you will probably come across in your reviews of articles will be non-experimental in nature, because that's what most researchers can do easily, and it's simply much more straightforward to just observe what people are doing and then measure their behaviors, attitudes, or emotions, for example. When we're able to measure multiple variables and show that there is a relationship between these variables, like the graphs we examined on the previous slide, then we can make some statements about the relationships of those variables. However, this is different than an experimental method where the situation is tightly controlled to prevent environmental factors or other potential sources of influence from affecting what it is that we are trying to measure. Experimenters will take great pains to make sure that they can manipulate an independent variable in a way that occurs before a second variable is measured, so that hopefully we can get closer to a causation type of explanation, like A always leads to B, or A influences B in an obvious way. So in the non-experimental method, we can't make comments about causation because we're simply just observing how two or more variables coexist. In the experimental method, we are carefully ensuring that one variable is being introduced before the second variable is being measured, so there is some room to make some causal statements. Another way to describe the non-experimental method is to describe it as a correlational method or correlational study. As I mentioned a moment ago, this is not the ideal scenario where we would want to make speculative statements about cause and effect. Even when we're relatively sure that one thing probably leads to another, we should avoid making causational statements unless we know for sure through additional studies that are of the experimental method variety. One of the drawbacks that also faces non-experimental methods is the lack of control that researchers have over the situation that they are observing. Sometimes we refer to this as a third variable problem, which is another way of saying that an extraneous or outside variable, or even a confounding variable is what we call it sometimes, is something that we did not actually measure but may be interfering with our results in contributing to our findings in some way. One really silly example I talk about all the time is the correlation between ice cream sales and homicides. Ice cream sales are positively correlated with homicides, so at face value, we might try to make some causational statements, which would be obviously a mistake, of course. And we would also be ignoring a third variable, which could very well be summer weather. Hotter weather is also positively associated with increases in homicides and is also positively correlated with increased ice cream sales. Taking the discussion from the previous slide a little bit further, the take-home message is we have to be very thoughtful and try to consider what other types of variables might be interfering with our ability to fully understand the phenomena that we are observing and studying. So here's a graphic from the textbook that also outlines the problem using different examples of anxiety and exercise. So as you can see in the upper portion, there are arrows that point from exercise to anxiety and from anxiety back to exercise, making the directional cause of the relationship unclear. So looking at this, we might be able to say that people who exercise a lot are more likely to be anxious because anxiety might be fueled by their constant exercising. Other people might say that when people get anxious, there's a greater tendency to exercise as a way to cope with that anxiety. To make matters worse, people who have more anxiety, looking at the bottom part, may have higher levels of income and worry about things like paying bills and taxes and whatnot, but may have more resources to pay for things like exercise equipment and gym memberships. So, as you can see, there are some pretty complicated aspects to consider in the context of non-experimental methods. Typically in correlational studies, we're simply studying the relationships between certain variables and may not have the opportunity to necessarily manipulate any of the variables. The experimental study is different because one variable is definitely being manipulated, and this forms either a treatment condition that we would reasonably expect to lead to a different outcome compared to if we withheld that variable. So let's turn this into an example. Let's say we're going to do an experiment where we are interested in migraine medications. We decide that we are going to test the difference between three conditions, condition 1 being herbal supplements, condition 2 being migraine tablets from the grocery store, and condition 3 being no treatment at all. So the independent variable are these three levels: no treatment, herbal supplements, and migraine tablets. And this is because the experimental design determines who gets what, and then we measure the outcome, which is the dependent variable, and detect whether there are any differences between these groups. The dependent variable is the outcome variable, which is probably going to be something like whether the person's migraine was well controlled, or whether their symptoms were much less severe, or maybe even absent. I can't tell you the number of times that I've had students come to me with repeated confusion over the difference between an independent variable and a dependent variable. So I think that the easiest way to remember the differences is that a dependent variable is always going to be the outcome variable. When you're measuring outcomes for what you think a result will be, you're measuring a dependent variable. If you are measuring the effect of something like a treatment, absence of treatment, and manipulated situation, anything else that you think is going to create an effect, this is an independent variable. So please contact your course assistant or me further if you have continued confusion about what the difference would be between an independent and dependent variable. One of the things that sets experiments apart from correlational studies is not only the manipulated variable, but the control that the experimenter has over the situation that they are observing. They do their best to ensure that those third variables we mentioned before or other extraneous issues are limited as much as possible so that they can make more accurate statements about causation. Typically, we randomize the participants and we randomly assign them to one of those conditions, like the herbal supplement versus no treatment versus migraine pill conditions, for example. And this way we can get an accurate comparison. Randomization is important because it helps ensure that there wasn't any other reason why a particular person found their way into one of those three conditions. As we stated earlier, the issue of internal validity has to do with the ability to draw conclusions about causal relationships from any particular study. Obviously, this is going to be less important in a correlational study because maybe we're not interested in causation necessarily. But if we're doing an experiment, this is going to be of the utmost importance. So what we would be looking for in an experiment that helps us to have some faith in the internal validity of our study is the temporal precedence, meaning that we took great pains to make sure that one variable was manipulated before we measured the outcome / dependent variable. Second, that we can observe a variation in the relationship between at least two of those variables. And three, the tightly controlled situation of an experiment helps us eliminate those outside plausible alternative explanations. Okay, final slide. External validity is the extent to which a study can be generalized to those other populations and settings. So you have to really consider whether having results obtained from a highly controlled experimental situation is going to make sense in everyday situations or reality for that matter. Because the truth is we don't live in experimental labs, and so sometimes it can be different to make that linkage into real life. This is contrasted with something in between correlational studies and experiments that we call field experiments. These are still experimental designs by nature, but we exercise much less control over those third variables or extraneous variables that we described before. These situations do exist, but in order to make more statements about generalizability, we have to give up some control over the cleanness of that experimental laboratory situation. So finally, one last piece of information is this concept of participant variables. These are the things that we cannot manipulate or easily change, such as a participant's age, their relative cultural understanding, their intellect, and so forth. And I know that this is a lot to take in, that understanding research may not come easily for a lot of folks. Quite honestly, it did not come easily for me in the beginning either, and it took a lot of practice and rereading and discussion with my professors and course assistants to get there. So please don't be afraid to ask for help if you continue to have confusion.